model. So for classification and regression, we can go with measuring the errors and revisit and validate the model by improvising it. If you choose any unsupervised or any other learning methods, accordingly the measure should be chosen and validate the model. So in the next sessions, we'll see in detail about unsupervised learning by Dr. S. Mognavalli. So develop any learning algorithms trained on one distribution, and it has to be generalized one to the other one. So this is all about a short brief about the machine learning techniques and the supervised learning methods, especially the classification. And we have seen how a decision tree could be built. Thank you. Any clarifications?
Thank you so much, ma'am. Awesome explanation. Hope everyone got some knowledge on machine learning, supervised learning, and class. Thank you once again, ma'am. Thank you so much.
Thank you, Aisha.
Thank you, ma'am. I take this opportunity and honor to introduce Dr. S. Mohanavalli, Associate Professor, SSN College of Engineering. Dr. S. Mohanavalli has 5 years of industrial experience and 21 years of teaching experience, including 12 years of research experience in the field of data mining. She received her BE degree in Computer Science and Engineering from GCT Coimbatore in 1992 and ME and PhD degrees in Computer Science and Engineering from Anna University, Chennai in 2005 and 2016 respectively. She started her career in teaching field as lecturer in 1998 at M&M Jain Engineering College and joined SSN as a lecturer in 2001. She is a member of Machine Learning Research Group of SSN, member IEEE, life member of Computer Society of India CSI, and Indian Society for Technical Education ISTE. Her research interests include machine learning and pattern recognition, data mining, and data analytics. She has more than 25 publications in reputed national and international conferences and journals. She received Best Teacher Award in M&M Jain Engineering College for the year 2002-2001. I request Dr. S. Mohanavalli ma'am to address the gathering with the topic unsupervised learning. Welcome, ma'am.
Hello.
Hello, ma'am.
Hello. Hello. Am I audible?
Yes, ma'am. Welcome, ma'am.
Yeah, thank you, Aisha, for that nice introduction, and good morning to all. So, can I know the audience, like is it students or faculty or mixed crowd? Hello. Okay.
It's audible.
Okay. No, you had a session on supervised learning. Did you have a break or can we continue? I just wanted to know. Shall I proceed? Yes, ma'am.
Yes, ma'am.
Yeah, I present. Is the presentation visible? Yes, ma'am. Yeah, can I proceed? Fine. So once again, good morning to all, and this talk I would like to
say it is actually the presentation is an outline of what is supervised learning, or rather it is going to give you the scope of unsupervised learning. So now you would have heard about supervised learning, right? So it is going to, it would have told you what is to be learned and how it is to be learned, right? So how do you do learning and what is it you learn and how do you apply learning? So you would have understood how to develop a prediction model or a classification model and how to apply that model to in future data for future predictions or classifications. Now you are entering a different scenario where the world is going to be unsupervised. So this unsupervised learning is not new to you. So from the day you are born, you are doing it. Okay, so it is a very natural phenomena where you learn things on your own. You discover patterns or you understand things on your own. And it's like, for example, you walk into a forest, okay? You don't know the names of all the trees, but you can try to differentiate it based on the type of leaves, type of flowers, or its height, or its the broadness of the trunk, something like that. So you try to relate what you see with respect to what you already know, right? So the concept of relativity is very much useful here in trying to understand things that is happening around you. So that is totally unsupervised learning. So it is a very natural phenomena. So that is that which is going to be written as algorithms and applied on large data sets. So which will really give you or help you to uncover the patterns that are hidden in large data sets, right? So in other words, this is also called as exploratory data analysis. That is, you try to understand the nature of data, yes, and the structure of data, so that based on which you can take some decisions, right? So you don't predict something, you don't classify something, right? You only simply you go with the data and try to understand what it is all about. So where is this applicable? So in other words, I've just represented this as data without label, because if you have to technically define unsupervised data, it is going to be handling huge data sets which comes without label. So just before the session, you would have heard from Purnima madam about training, testing, things like that, where your data set comes along with labels. That is, you are given a set of features to describe a data and what is the name of it, what is the group of it, what is the class of it. Like this, the class label is also available to you. So here you don't have such labels and you are going to actually create a label, or you're going to discover the patterns in data and apply a label to it, right? So you're going to attach a data set to a label. So that is what is actually unsupervised learning. So what are the challenges? So here the challenge is, it sounds very simple, right? You are going to simply explore data and try to understand it. So now, who will validate? So the important challenge here is, when you compare this with the supervised learning, there is somebody to guide you. Somebody says, see, for example, this is apple, this is tomato, this is orange. Slightly all are looks like a ball only, but slightly there are some differentiating features there. And somebody will tell you this features only differentiate an apple from a tomato or things like that. So next time when you are able to identify a tomato as a tomato or apple as a tomato, somebody will there again to say that no, it is misclassified, it is correctly classified. So there are validation schemes which is going to make you to learn easily. But here there are no such validation schemes, and because the data set comes without labels, right? And there is no objective, because it's a very natural phenomenon. You don't know what you are searching for. You are given a large, huge data set, but I don't know what am I searching for. You are given a bank database with data about billions of customers, but you don't even know it is a bank data set, right? So likewise, there is no clear objective of what you are going to do, how you are going to do, and there are no validation schemes to actually justify or correct your clustering technique. Okay, fine. Now, where do we apply this unsupervised learning? So, what is the real-time scenario where I can apply unsupervised learning? Right. So, I told you just now an example of bank database. So, if I'm looking for groupings, I want to simply segment that data, or I want to find out whether there are some similar occurrences in that data. Maybe people who are all taking educational loan, people who are all buying cars, people who are all getting credit cards. Likewise, there is possibility of finding similarities or groupings in a data set. Then maybe based on the group which I discover, I can take a decision. I have a student database. I'm able to identify groups, maybe hostlers who are doing well in studies, who are not doing well in studies, things like that. So depending on the groups which I get, I may take a decision. So likewise, there are situations where I can look for similar groupings in a given data set. That is called as clusters. So the first application or the foremost application is to identify clusters. Clusters are nothing but similar groups in a data set. Next is, the other way, it is simply the opposite of clustering, anomaly detection. That is, there may be a data set which is where most of the data set belongs to one category and there may be some outliers. Same bank database, there may be one or two loan defaulters, fraudulent customers who will get a credit card and not pay the due, things like that. So majority will be okay. Maybe there will be one or two data points which are does not belong to the common crowd. So in such cases, you will be interested in finding out the outliers in a given data set, because there you want to catch only the fraudulent customers and attack them. So like that, it may be network intrusion, it may be a disease spread or something like that. So where things are abnormal, you are looking for the abnormal patterns that becomes anomaly detected. So here also you have to very stick on to the definition of unsupervised learning. Nobody is guiding you. You are only separating the data into normal and abnormal. And because of very few data points are abnormal, you are interested to find out why they are abnormal and they are going to take some decisions. Another interesting application of scenario is association mining. That is, if you want to relate occurrences of activities, disease maybe there is a side effect. One person is taking a medicine, maybe he is prone to buy one other medicine because he will get a side effect of that medicine. Okay, so all your web clicks, you visit one web page, you visit another web page. You like recommendation systems. Okay, likewise, if you are prone to you're interested to identify associations or relationship between set of activities. Okay, then in such scenarios, it is called as association mining. There also unsupervised learning only will help you. And then you have dimensionality reduction. That is, when you have a huge data set and you want only the relevant attributes. For example, to predict the disease of a particular person, his name or his address is not required, or his phone number is not required. Only the clinical attributes or his height, weight, his blood group, things like that. Only those things are going to be important rather than other attributes. So if such cases, if you want to reduce the feature set and take only the relevant features, you may go for dimensionality reduction techniques. So there also the unsupervised technique will help you, because you stick out to the definition. Unsupervised learning techniques are applied to data sets without labels. So these scenarios, even without labels, you can carry out these activities. So these are the important scenarios where you can apply unsupervised learning. Okay. So the same thing I've given it differently. If you, you may have continuous data, you may have categorical data. Okay. So in the case of continuous data, you will apply clustering techniques. In the case of categorical data, you will apply association and sequence analyzer like hidden Markov models. Okay. Fine. And the scope of this presentation is, I told you, unsupervised learning is a ocean, right? So obviously we will not put everything in 1 hour and give it to you. So what I thought was, I will just give you a scope of unsupervised learning. So the scope of unsupervised learning is broadly this: clustering, anomaly detection, association rule finding, and dimensional reduction. For each of these scenarios or each of these applications, you have a rich set of algorithms written by all our researchers who have done research during the past 50 years in all these areas, and you have a wide collection of algorithms for each of these activities, all of which operate on unsupervised data and is going to extract patterns of the given data. Okay. So the focus of this presentation will be, I will be touching upon one unsupervised learning technique, that is clustering, and tell you what are the different clustering techniques, and I will expand, or I will just explain one clustering, partitional clustering technique. So the agenda or the outline of this presentation will be, you will be introduced to what is unsupervised learning, applications of unsupervised learning, and then we'll touch upon what is data clustering and what are the characteristics of good data clustering when it is done in a better way. And then we'll also go through one algorithm, one partitional clustering algorithm with an example. Okay. Fine. So, what is clustering? So, as I told you, if you are looking for similar groups in a data set, then you call such groups as clusters. So, in a student database, I want to group them into good, better, and or good, average, and bad. It means good means people who are learning on their own, or they will definitely manage on their lessons and get above 80%. And those with some hand-holding guidance, they will manage to get somewhere between some 50 to 80. And those students, even if you put any attention, they are not going to perform. You are going to brand them as bad students. We can see that given a student database with the marks, easily you can categorize students into groups, right? So likewise, just for you to understand, if there are student community, just I'll just give this example. As I told you, you can take any application from underwater application to astronomy. So anywhere, if you are having abundant data and you are interested to find out the similar groupings, then you can call that groups as clusters, and identifying such clusters is that activity is called as clustering. Okay, so clustering is a unsupervised learning technique where you don't have any class labels. Okay. Right. Fine. The same is the diagrammatically explained here. So you can see that. Hello, Purnima. Hello.
Yes, ma'am.
No, I just want to check whether it is audible and the screen is also.
Yes, ma'am. Yes, ma'am. It's audible.
Okay. If anything is wrong, maybe you or Aisha can interrupt and tell
Yes,
me.
ma'am. Sure, ma'am. You'll carry.
Okay, good. Thank you, thanks a lot. So you have, I am just representing the same definition of clustering, just mathematically here. Very simple maths, I have not included any equations here. So you can see that any data set is going to be represented as a set of points x1 to xn. So these are data points. I am going to represent this set of data points as x. That's it. So now what is it we are interested? We are going to apply some function, mathematical function on this set. You can even see this as every x can be a set of features. So this will be a 2 by 2 matrix. So you will have n rows, every row representing one data point, and every column will represent one feature. For example, if I am going to represent a student as a data point, maybe I am going to include only his age, height, weight. Then if there are 50 students, then this x will be 50, x1 to x50. So I'll have 50 rows in the matrix, and I'll have only 3 columns in the matrix, just the height, weight, and the age of that particular student. Student number 1, whatever is his height, weight, and distance. So it will be a 50 by 3 matrix. That's it. Now I'm going to apply some algorithm or mathematical formula on this matrix, and I'm going to extract the similar groups or clusters. Maybe people who are of very tall, average height, or just below average height, maybe like this, or maybe based on the age, or maybe based on the weight, or a mix of 3 also you can do, who are height, who are also having a good height, good weight, and they are elder or whatever it is. Then they may be grouped. So depending on what is the population you have, likewise only it will be grouped. Okay. So if there are not 3 classes, there are only 2 classes. People who are very tall and people who are very less tall. Only 2 groups you have, then you will have only 2 clusters. Because I am not giving any labels here, I am not also not mentioning the number of clusters I want. Okay, so whatever is existent in the data, you may also end up sometimes clustering and you cannot find out. The data is simply scattered or sparse and you cannot find any groups also in the data. It doesn't mean that it is a failure. You are understanding that there is no clusters or no clusters existent in the given data. That is it, right? So, so clustering is about, as I said, applying a mathematical algorithm or a formula and finding out, trying to fit your data into that mathematical equation, and to find out whether there are any similar groupings in the data. So this is very simple terms and explanation of clustering. Okay. And some applications. So as I told you, you can pick any application wherever you want. There are possibilities of having groupings. You can apply clustering algorithms. So you can see that you have astronomical data set. So if you want to find out any constellation of stars or any abnormal behavior in a recently you have seen this Saturn and Jupiter coming together. So that some abnormal activity happening in the space. So you want to find out such things. So you can definitely apply clustering. Social network analysis. I want to find out the most influential group, your friends group. Okay. So certain people will be together, they'll be tightly bounded. It means, for example, they're all very close. Okay. So like this, if you want to find out the such groupings in a social network, you can use clustering techniques. Market segmentation. Take all the sales data, you can apply a clustering algorithm and find out which group of people buy what commodity or which product is going well in which particular area, right? So likewise, you can perform a in sales database also you can find out. Healthcare, you apply clustering techniques to easily segment any image. So you nowadays people are not relying on text data or clinical data, they simply take CD images or any type of microscopic images, or simply they rely on microscopic images and image analysis or understanding to actually do disease diagnosis. So there, if you want to find out again, you want to group your process your image and segment your image, you can apply data clustering. Right? So this is one more simple example where even a simple small what to say clothing store, people are going to segregate or categorize their own dresses according to your size. So here also there are some features. So you have the again length, breadth, color. So there may be so many features. So there is no one single area where you cannot apply clustering. So I visited all areas: medicine, psychology, botany, social. So wherever you want to identify groupings or you are looking for any similar groupings in the given data set, you can apply clustering. Fine. So that is all about generally what is clustering. So finding groups in the given data set is clustering. That's it. So I said simply I'm just adding the word similar. Later I'll come into a complete definition. Now what is this clustering? What are the different varieties of clustering? To do clustering is people, as I told you, this is more than 50 years old. So people have written many algorithms, and they have classified this set of algorithms into different categories. So you have partial algorithms, you have hierarchical clustering, you have vestibular-based clustering, you have probabilistic models. So if you can give, if I take a minute to just tell you what it is. This depends on the type of data set. I told you are going to apply clustering for a particular data set depending on the application. So depending on the application and the nature of data that you have, you can choose any one of these algorithms and try on that data set to get effective clusters or to perform clustering effectively. So if your data set is consists of spherical clusters, that is, there is easily linearly separable data set is what you have, and you can easily segment them, then you can apply partial algorithms in that data set. For example, your database. You're looking for different groups of customers. Okay, so you can apply partial clustering there. Maybe you have a data set which is populated or which has evolved in a hierarchical fashion. So you start with the entire college, then you subdivide your college into departments, then your department into sections. Likewise, you are having some hierarchy in the evolution of data itself, then you can apply hierarchy clustering. Then, if you want to classify a data, that is, your data set is not going to be exactly spherical. For example, you just think you want to find out whether there is some water body underneath the earth, or you want to check whether there is any mineral ore, or the spread of a virus. Okay, correct centera or spherical, you will not have a virus spread. So a person has got the infection, wherever he travels, to whom is going to contact, whatever is his travel pattern and contact pattern, only like that this virus is going to spread. So it's not going to be exactly spherical, but whomever he is close to. So wherever there is a proximity, then the other person will get a virus. They might have water body. If you have water body, then it is slowly spread. It will not directly spread into exact circular, it will not be a spherical body of water. So it may follow a river path or whatever it's right. So in that case, depending on the proximity of data points, you try to associate a cluster. So that is where you call that such type of clustering or such type of algorithm is able to identify clusters based on proximity of data points. It is called as density-based clustering. Okay. So here again, I repeat, I'm only introducing what are the different types of clustering. Each is going to have, because you can study clustering as one subject in a curriculum. Okay. So about clustering, about each of these type of algorithms. I have n number of algorithms under partial algorithms. I have many algorithms under hierarchical density-based things like that. So for different applications, there may be hybrid versions or different evolutions of these algorithms. So I'm just telling you in a nutshell what are the different types of algorithms, and depending on your need, whether you're doing it for education purpose or for research purpose or whatever application you're doing it, accordingly you can choose an algorithm and you can do a deep dive in this particular area. Okay? So probabilistic models, if you have a data population which you can fit into a particular probabilistic model like Poisson model, binomial model, normal distribution. Like that, if your data population is tend to fit to a probabilistic model, then you can go for probabilistic clustering techniques. So likewise, if you have some base idea about what is the data, how the data has evolved, how it has grown, and in what aspect you want to analyze the data. So again, it is all the same. You have a huge collection of data, you don't have any labels. But if you are able to at least if you are at least have an idea about the nature of the data, then you can choose any particular algorithm that is applicable, right? So now in this presentation, we will go in the course of understanding partitioning algorithms. I will be touching upon one type of partition algorithm, very popular algorithm, the K-means algorithm. Before which I want to also share the characteristics of clustering. So partition clustering, the desired characteristics of this clustering is, I told you this no partitional clustering is going to be applied to a data set which tend to have spherical clusters. So I have told you one example, for example, your student database or a random database. Okay, so where you are looking for groups of people who are doing the same thing. Okay, so for example, the bank database, right? So here, since I am looking for spherical clusters or data nature is such that it has spherical clusters, for such type of data sets, partition algorithm can be used. Okay, so the characteristics of such an algorithm is the cluster members should be well represented by its centroid, because by means of cluster, I am not going to give information about all the points or all the people who are belonging to one group. No. For example, if I am going to form a group that people who are prone to already obtain car loan, maybe there are 1,000 people or 2,000 people who have got car loan, but I will be only representing this group of 2,000 people as a single data point. Okay, so if a person is of the age in the group of 35 to 40, he works in IT, he earns more than a lakh. Okay, he has not much experience, he travels. So how do you put in our pictures? Okay, so if such similarities are there, they tend to go for a car loan. So if that is the case, then I will be giving one set of or one feature set as the representation of the cluster. Okay, and this cluster should be stable, well separated and compact. So as I told you, similar nodes will be there. So other representation or the other technical representation is well separated and compact. So what is well separated and compact? Okay, so you have data points here. So the distance between the points that belong to the same cluster is called as intra-cluster distance, and the distance between points that belong to two different clusters are called inter-cluster distances. So a clustering is good when intra-cluster, that is the data distances between points within the same cluster is small, least. The distance between data points that belong to two different clusters are maximum, are huge. Okay, so distance of data points within the cluster should be less, and the distance of data points across the cluster should be huge. If that is the case, then your partitioning algorithm is working well and you are doing good clustering. So this, okay. So how do I find out the distance? I'm telling repeatedly something. I'm telling about distances. Okay. So how do I measure the distance between two different data points? Now I told you a small example. I'm going to store this information about 50 students. I'm going to store height, weight, and their age. So I want to now compare student 1 and student 5. What I will do, I will find out the difference between their height, find out the difference between their weight, find out the difference between their age, and simply add. That is sum of squared error. Okay. And if that error is very minimum, then they both belong to the same cluster. Otherwise, they do not belong. Right? So how do I now find out the distance? There are so many distance metrics depending on your application. So we will not go into the math here. As I told you, if you have numerical values, the popularly used distance is the Euclidean distance, which I discussed just now. Difference between the attribute values, that is height minus height, weight minus weight, age minus age, and then all the differences are going to be squared and you take the square root. Okay. So you either use the true norm distance, that is directly use it, or you are going to take the square root and use it. Okay. So that is Euclidean distance, which is very popularly used to distance matrix. If you are using a text data, you have distance matrix for that. If you are using speech data, you are going to have different, or you are going to have an image. Depending on the application and the data set that you have, you have a number of distance matrix. Okay, so you can choose an appropriate distance matrix to calculate the distance between any two points. Right. So now this is how you find out the distance. Right. Next is, what are the other aspects of clustering which you should take care of? You just saw in this thing that you should have minimum within cluster distance and maximum between cluster distance. So in the within cluster distance is called as withinness, and the between cluster distance is called as betweenness. So withinness should be less and betweenness should be huge. Okay. So I'm going to take only a ratio of this withinness and betweenness. So if I say withinness and betweenness, then withinness is small, betweenness is huge. In that case, you should have a very least value. Suppose the ratio between betweenness and withinness, then the value which you should get should be huge, because it is betweenness should be very huge, and that you are going to divide by withinness. So anyway, either whichever you take, always the withinness should be less and the betweenness should be high. If you are getting such a result in your clustering, then that clustering is very good, right? So the aspects of clustering, as I told you, your clustering quality will be good when your intercluster distance is maximum and the intracluster, that is betweenness, is minimum. Withinness is maximized and betweenness is maximized and withinness is minimized. Okay. So now why are we doing all this? Because we don't have any labels. In the previous session, you would have seen that you had an external index. That is, it means what? The data set is given with label. Okay. A particular set of data along with whether, for example, the climatic condition, and you say that whether this situation is good to play or not, something like that. So like you have a set of features and you have the result also with there. So it means you are having the label. So if that is the case, then you can apply your clustering algorithm and check whether the label is correctly assigned. Okay. So group A, group B, group C, after the clustering, whether you are getting the correct label, you can find out. That is if you have the external index. But we are talking about what? Data set which is unsupervised. That is data set which does not have label. So I don't know how to validate whether what I'm doing is correct. So when I apply a clustering algorithm, am I choosing the correct clustering algorithm? Am I doing the clustering correctly? Am I getting the correct number of clusters? And apply clusters, whether it is good or bad, is it compact or not? So many quality aspects which I can take care. For which only you have this internal index. So here also there are around more than 50-60 measures which is called as cluster validity indices, CVI, cluster validity indices. And many people have done research in this aspect also, and they have populated so many measures to say whether a given cluster is good or bad. Right? I have taken the very simple cluster validity index for you to understand in the beginner stage, and maybe later on all formulas will be a version of this only. It will be a modified version of sum of square error only, but the basic version is sum of squared error. As I told you, you are going to take the difference between one point and the other point, and that error is going to be, you just square that error and add up all the distances. And if that distance is going to be least between two different points, then you put it the same cluster, so that the distances between points within a cluster will be less. And the distance between the points across two clusters will be high. Okay. Now, how do I find out how many clusters exist in a data set? We are talking about what are groups, what are similar groups, what are the technical meaning of similar is it should have good withinness, that is least withinness and better high betweenness, so that the ratio of them is going to be used to measure the cluster validity index. So whether a cluster is good or bad and decide. How do I decide how many clusters exist in such a data set? So what you do here is, you can see in this graph, you are going to start with what is the minimum number of clusters a data can have? It should be at least, you should be able to partition it into 2. So you start with 2 and you can simply proceed. Okay. Generally, it is n by 2. If I have 50 points, I can proceed till 25. K is equal to 25, I can proceed. So for every iteration of K, I find out what is sum of squared error and I plot. Okay. So I plot this graph. So this plot, wherever it takes a bend, for example, in 5, when K is equal to 5, this value, it is dropping and then it is taking a bend. So this data set is prone to have good clustering results when K is 5. It means what? There are at least 5 good clusters in this data. Okay, so this diagram is called as elbow diagram. So this is the very simplest way of finding out how many clusters exist in a data set. Okay, so as I told you, you should know what is how to compute withenness, how to compute betweenness, and then compute the ratio of it. Or you can simply directly plot the sum of squared error that occurs so that you get for each value of K value, and you plot it, and wherever there is a bend, for whichever K value you see the bend, you can take that as the best number of clusters available in that data. Okay, so this is one more aspect how you can find out the number of clusters in a data. Okay, the same withenness and betweenness is now here technically defined as cluster cohesion and separation. You know, less cohesion, it is compactness of the data. So it can be measured by the within cluster sum of squares. It means what? So it is simply the sum of distances between the points within a cluster. That is called cohesion. This is the distances between points in one cluster and the other cluster. So you take one cluster, you take the sum of the distance of all the points within the cluster, you call it as cohesion. And you compare one cluster with the other cluster, and then you find out the distance of all points with respect to all other points residing in the other cluster, and you find out the separation index. So this ratio is now going to be used in finding out the number of clusters or the validating whether a cluster is good or bad. Okay, so I am just again going to tell you something about what is Silout index. It is a Silout index is one other cluster validity index which is going to be used to find out the best K as well as to find out whether your cluster is valid or not. Okay, so combining the cohesion and separation. It's what cohesion is? Compactness or withenness. Separation is betweenness. So I have used simple words initially to make you understand as to what is it actually. Other technicals I'm just using it. So then when you later on go and study about Silout coefficient, you will know what are these terms. So here also you can see that there are two clusters. I mean, you have the cohesion or the withenness of a cluster computed as A, which is the sum of distances of all the points within a cluster, and betweenness is distances between the other clusters. So this, you know what you do? You take the ratio of A is to B. So A is to B is very small. While A is withenness, it should be very less, and B is betweenness, it should be very, very high. So this ratio will be very small. Another, they subtract it by from 1. Or you can directly take it as B minus A by 1. Why? Because B will be, if you take the ratio the other way, B will be high and A will be small. So you will get value more than 1. So you have to subtract from 1. Okay. So however you take, if you take A by B, you have to subtract from 1. If you take B by A, then you should subtract 1 from the value. So whatever it is a kind of normalization. You will get the value between 0 and 1. And the closer the value, Silout index closer to 1, then your clustering is good. Okay. If it is nearer to 0, then the clustering is not proper. Withenness only it is high. The betweenness is less. So you can do better clustering. There is possibility of improving your cluster. Okay. So this is about cluster validity in Silout index, which is a cluster validity index. Right. Now coming to the K-means clustering. So I am just assimilating whatever I told you. I have just introduced what is unsupervised learning comparing to supervised learning. So here nobody is going to tell you what you are supposed to learn, how you are supposed to learn. So learning eppadi pannanum yaar solla poradilla, edha pannanum edha learn pannikkanum solla poradilla. You only given thrown a big data set without labels. Okay. So if such is the scenario, what all you can do? You can go for either clustering, or you can go for association rule mining, or anomaly detection, or you can go for dimensional prediction, depending on your need and application. Right. Now, in the scope of this presentation, I am just focusing on the first technique, which is clustering. So what is clustering? I've told you given the definition of clustering, I've given you the applications of clustering, and I've told you some technical aspects or quality aspects of clustering. So just like that, because it is unsupervised, you cannot do blindly what you want to do, right? So if you want to do something effectively and you want to get some resultant clusters, what is it you have to be keen about? So you should check on whether the data set, what you take, okay, is categorical or continuous, and depending on that, what is the type of clusters that may exist in the data. So which type of clustering algorithm we should use, partitional, hierarchical, or density based, whatever it is. And accordingly, if you proceed also, what are the qualities of clustering? So if you are going to retrieve clusters from a data set, that cluster should be compact, okay? So it should be highly cohesive, it should be well separated from the other clusters, and the cluster, whichever the cluster validity index you choose, should satisfy that. And then depending on the cluster validity index, you can make a plot and draw a Go diagram and find out the correct number of, or approximately correct number of clusters that may exist in that data. So up till now, we have discussed the types of clustering and we have discussed what are the quality aspects of clustering. Now we will touch upon one important popular algorithm, partitional clustering algorithm, by named K-means clustering. So this was way back in 1960s, that is more than 50-60 years before this algorithm was coined. So this is a very simple algorithm. Sometimes it is also used as a pre-processing technique for today's advanced applications. When you have huge data, you can apply K-means algorithm as a pre-processing step and filter out only the required clusters and then work on that set of algorithm. For example, image processing, medical image processing application work where you have a set of tumor images. Now you are interested only in those images which has tumors. So then you have to apply a K-means algorithm as a segmentation technique on your data set. Segment only those portions which has tumor, which you can call it as region of interest, and then you can work on that data. Instead of working on the entire abundant data set, you can only pick your region of interest and then do it. Finding satellite image process, it is very costly to get an image, and it lot of pre-processing already to be done on a satellite image, right? So on the remote sensing images, you can apply this K-means algorithm as a pre-processing technique, extract the region of interest, and then continue to work on your application. So it's a very simple algorithm as well as a successful algorithm. So what happens here is you are going to divide your data into K groups. That's it, one line. Okay. So you go through all the algorithms. I will take very simple example. So here what you do is, because you want to divide your data set into K clusters, I am going to choose initially K data points as the initial centers. This was the first 3 last 3 random any for example, if my K is equal to 5, I will pick 5 data points of the given data set. And the student database approach where I want 50 students, I have 50 students. For each student, I am having height, weight, age as the attributes. Very simple. So I don't know how many groups it is going to form. Okay. So, but I am interested to find out. Maybe I can apply all these formulas what I told you. I can calculate absolute index, or I can calculate sum of squared error. Somewhere I got a diagram. I find out there are 5 groups in that data set. That 5 in a correct approximately. There may be some 5 approximately or 5 sensible clusters I can take from that data. What I do. So I have to now, I don't know how I can group them. I'm only having the data set. I'm not having any tables. But I know by applying some cluster validity index metric, I know that there tend to be 5 clusters in the data. So what I do, I randomly pick 5 student details. So 5 rows in a random, right? Maybe first 5 rows or any 5 rows from that data. Okay. Then what I do is, for each center, now I'm going to call all these 5 points as centroids. So C1 to C5. I take C1, comparing to this C1, I calculate what is the distance of the first student with this centroid. How do I calculate the distance? Height minus height, weight minus weight, age minus age. Reference another C1. So C1 is a reference. I'm going to calculate the distance of all the remaining 49 student data with this, find out the distance. If the distance is, okay, I do this for all the 5 clusters. So I have C1 to C5. I take student 1, I compare student 1's data with C1, C2, C3, C4, C5. I get a very least distance. I associate student 1 to that cluster. I take student 2. Student 2 is again, height, weight, age is again measured with C1, C2, C3, C4, C5. Whichever is least distance, I associate student 2 to that center. Likewise, I do for all the 50 points. Okay. So after this, I would have randomly separated the data set into 5 groups. Maybe C1 has 10 records. C2 has only 3 records. C4 have 15 records. Likewise, depending on their closeness, their proximity, maybe they are of same height or same weight or age, or factor, they would have put them in the same cluster. So I have randomly now distributed these people into 5 different groups. Now I will take the actual mean of these 5 groups. That becomes the new centroid. So this is what I do iteratively. Randomly choose k data points, assign each data point to the closest centroid, recompute the centroids and repeat it until convergence. Now what is convergence? Same thing is written here in abstract view. I've just written the algorithm here. So same points only are there here. So now when do I converge? When will this get converged? Either you can fix the number of iterations. I will do it 10 times. So 10 iterations பண்ணிட்டு என்ன group கிடைக்குதோ அதை வச்சுக்கணும், depending on your computing ability. Because if you are having billions of customers of a bank database and you cannot do hundreds of iterations, so you can fix number of iterations. 10 iterations எத்தனை cluster கிடைக்குதோ அதை நான் வந்து output வச்சுக்கணும்னு சொல்லி நீங்க அந்த compromise எடுக்கலாம். இல்ல I want perfect clusters. It is a medical image data or some important data where I am looking for correctness of the data அப்படின்னா then you can have the error factor. அதாவது previous centroidக்கும் new centroidக்கும் you can set a threshold. So if the new centroid is same as the previous centroid, then இதுக்கு மேல அது வந்து saturated. You cannot further proceed to iteration. Then you can have such, or you can have a threshold value until the difference between the previous centroid and the current centroid is that threshold value. You can continue your iterations. Likewise, you can set terminating conditions for your convergence or stopping condition for your clustering process. Okay. Now what is the strength? So as I already told you, this is a very simple algorithm, easy to implement. You can implement in any language you want, okay? And the time complexity, you can say it is T, K, and N. What is K? Number of clusters. What is N? Number of points. What is T? T is the stopping condition. What is the time taken for you to stop? The convergence, how many times are you going to run this? Okay, so that is your T. So this is the time complexity. It is very, very simple algorithm. And so as I told you, the disadvantages is this K-means algorithm is good only if your data has spherical clusters. Okay, so if your data is not spherically distributed and it is going to be sparse, then K-means algorithm will not give you good results, and it is very sensitive to outliers. Why? Because see, the centroid is what? It is the mean of a cluster. So statistically, mean is a very sensitive parameter. In a median, it will be robust. Okay. But if you take mean and you add one more value to your data point, definitely the mean will change. Okay. So that is the reason as to when there is an outlier, the cluster centroid tends to change frequently. So it will not get saturated, or it will not easily converge if your data set has outliers. Right? So if you have outliers in your data, that may disturb the convergence of your K-means cluster. So if your data is sparse, or if you don't have spherical clusters, or if you have outliers, this algorithm may not give you ideal clusters. That is a disadvantage of K-means algorithm. Okay, and K, finding out K is the biggest challenge in K-means algorithm. Okay, so I already told you one method, right? So all the methods are approximation methods. Actual data set which you have, whether it will obey what you say, I don't know. You also don't know, because it is totally unsupervised. So coincidentally, if your data set is going to abide by whatever mathematical formula you are applying on the data set, then there are chances that the K value you choose may be right and you may get good clusters. Right? So we have to wait and watch only there. So people have, as I told you, have actually done a lot of research in finding out K. So finding out K beyond K means beyond 50 years, the finding K. There are so many papers. Even now today it is an open research problem as to how to find K, how to find the ideal number of clusters in a data set. So these are all again similar to the Silhouette index. These are all indexes, or rather the cluster value index. There are so many mathematical formulas, so mathematical indices. That is cluster value indices found out by many people. But ultimately, the bottom line statement it will be a ratio between withinness and betweenness. Okay, so the distance within the cluster and the distance between two clusters, across clusters. So if that is going to be, that ratio is going to be good, then you get good clusters. So the ratio correct, people have done a lot of research work, and people have also listed out so many cluster validity. So even if you pick R, there is one package called NB clusters, number of clusters, 54 index. So you can try out, if you simply run that package, it will run all the indices and tell you what is the best value of K for a given data set. So for one metric, from one metric to the other metric, the number of clusters also may vary. Finally, people also have done research where they'll apply different cluster validity indices, and whatever K they get, they'll take an average of that K and then find out what the approximate, or to say the nearest value for K. Okay. So if we have time, I'll just very quickly run through one simple example. So all of you would have heard about this data set, IRIS data set. This is also very old data set, which consists of data set information about 3 different types of flowers of the iris plant, named as Setosa versicolor and virginica. So I just put the images of these flowers. So this algorithm was coined in an era where there was no sophisticated image processing algorithms. Image processing algorithm, image processing, you can classify the images to watch what is the type of flower. But then people didn't have very good image processing techniques. So what they did, they measured the petal width and height. So petal is here, sepal is here. So they will measure the petal and sepal height and width in centimeters, and they will represent one flower as 4 features. Or petal length width, sepal length width. That's only 4 features will talk about one flower, and they stored it like a table like this. You can see that you have 150 data points. It means it is information about 150 flowers. So 50 flowers belong into one class. Setosa 50 Setosa flowers, 50 versicolor flowers, and 50 virginica flowers. And you can see that how are they representing the data as a feature vector. What is a feature vector? So the sepal length, width, petal length, width. So these 4 information about that is measured in centimeters and stored as a record. So this is one record, this information of one flower. So likewise, they will store the. Now, why people are using this data set popularly? Why? Because this is noise free and it does not have any missing value. And to most of the algorithms, if you want to, this is a benchmark data set which was donated to the UCA repository, that is University of California Irvine repository, way back in 1936. You can see. So since then, people are using this data set as a benchmark data to validate their algorithm. Okay, fine. So this data set, if I'm going to run it using a K-means algorithm, using in Python, using the NumPy package, there is a K-means input function. If I use that and if I cluster this data with K is equal to 3 and visualize it, so I get this result. So you can see that this is well separated. Okay, this is this flower. This is very different, right? This Setosa will be very, you can easily discriminate, you can see that. But there are some similarities between versicolor and virginica. These are identical, there may be many misclassifications. So you can see that here itself. Okay, so this is your Setosa and this is the virginica and versicolor. There may be some overlap also here. On an average, you get around 80%, 80-85% clustering results for this data set. Okay, so this is all I have about to give you about outline about sorry. So this is my presentation giving an outline overview about unsupervised clustering. So if you have any questions, I can take. I will share this presentation and mail ID with Aisha.
Thank you so much. Thank you for
Thank
spending
you all.
your
Thank you all.
time with us.
Thank you, ma'am.
Really a wonderful explanation on cluster, K-means, their strength and weakness, and example on iris dataset. Thank you so much, ma'am.
Thank you, Aisha.
Thank you, ma'am.
Thanks for the opportunity.
Thank you so much, ma'am.
Yeah, convey my thanks to HOD, Satyapriya, and all who are involved in this program.
Thank you so much, ma'am.
Thanks, ma'am.
Guys, thank you all, and kindly join me shortly at 2 p.m. for afternoon session. Gentle reminder, e-certificate will provided to everyone. Join me shortly 2 p.m. for afternoon session. Is about machine learning to deep learning, and feedback form will be uploaded in the chat box on afternoon session. Kindly join soon, guys. Thank you.
Thanks, Aisha. Can I leave?
Yeah, ma'am. Thank you so much, ma'am.
Okay, ma. Thank you. Bye.
Bye, ma'am. Take care. Thank you, Purnima, ma'am. Thank you so much.
Thank you, ma'am.
Thank you, ma'am.